Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody watching us from the future. Today I will hopefully finish this part of the lecture, which is a bit, as I said, a parenthesis in the middle of the lecture because it's not really new material or new technologies. It's just a few tips and tricks when you program at large scales. What I mean with program at large scales, of course, here is not program with a SQL or a high-level language, but when you have to actually put your fingers into C++, Java, Python, so the imperative languages that give you very fine-grained control about what's going on. And what I have in mind in the sort of code that you're writing, you're basically implementing the physical layer of some higher level database. So you might have users up there that write declarative languages, and you're a data engineer, and you have to write codes that is going to be running at large scales. I have in mind typically the people working in large companies also like Google who have code that gets executed billions of times, trillions of times because of the massive scale that we're talking about. And so I left you with the idea that before you try to put more money, more machines, more memory, more CPU, it's tempting to do this, right? But before you do this, you should try to use what you have. And you will see that it's extremely rewarding because it's incredible what you can do even with a single machine, with a single laptop. I like to use the example of one of my former students, Marco, who had a small laptop, and it was absolutely perfect because that gave a framework for trying to squeeze everything you can in performance from a little machine. And then, of course, when you have done that and you take it to a cluster, it's magical because then you get incredible performance. So I left you yesterday with how to avoid memory scale-ups. So again, the idea is that you have to scrutinize your code and find the classes that get instantiated billions or trillions of times. You have to check in these classes what is every single field that you have. Do you really need them all? Do you have the most efficient types? For example, in data structures in Java for sets, for lists, you have plenty of implementations for maps, right? For maps, you have tree maps, hash maps. For lists, you have array lists, linked lists, and so on. They all have different footprints in memory, right? And depending on your use case, you might prefer one or the other. You can also run some small experiments. But you really have to do some clockwork to find the most memory efficient ones. Do you have anything redundant? Do you store the information twice? If yes, then you can maybe be less redundant. It will cost you more CPU, of course, because if you remove redundancy, you might have to compute more on the fly. But it's okay, because that's what you do when memory is the problem. So if memory is the problem, then it's no problem to consume a bit more CPU, right? So then you have to remove redundancy and again, avoid inheritance. The style guides at company, last time I checked at Google, it's forbidden to have subclasses. You know, you only allow interfaces or abstract classes. I don't know if it changed, but it has to do with this kind of considerations that takes memory and it's also less performance. Now, what about the CPU? Here, what I'm about to say could come as a shock to some of you because many of you probably took object-oriented programming lectures. Where you learned very good things, actually, how to write good software, how to write reusable software with reusable components, with encapsulation and so on. And of course, these are very, very good techniques, right, for writing. I'm not putting that into question. What I'm saying is that when you deal with code that gets executed billions of times, then you have to give up on some of these things. When you write systems code, when you write very large-scale code, then some of the things that you learn in object orientation need to be reconsidered, right? So for example, it's nice to have plenty of method calls and to factor your code, but if you have too small methods and too many method calls, that eats up CPU whenever you call a method. Of course, the compiler can sometimes inline and find out ways to optimize, but not always, right? And so maybe if you inline things or if you have a bit larger methods, you have more control about the fact that it's not going to eat up too much CPU. If you have subclasses, which I already told you should try to avoid, but you have overridden methods, that also eats up some CPU clock, right? When you have to resolve overridden methods. If you have a flat hierarchy, you don't have that. You just directly call the method and that's it. You don't need to resolve anything. are you overusing class hierarchies, right? If you have a class hierarchy with 15 different levels because you overdid the reuse and the inheritance, then this is going to slow down your system. In fact, it's also going to slow down productivity of your teammates and the people working on the product, because you have to imagine when you overuse inheritance, that to change one thing, you need to open 15 files and modify small things in plenty of files. That has an impact also on productivity. Then instance of casting that also eats up CPU. And you know, again, it's a shock because I'm telling you the opposite of what you're told, right? That you should use a switch, right? This is the most physically efficient way that you can handle this without triggering all the machinery for the type system and inheritance, right? So for very large scales, we love switches. We love some things that are very simple, easy to understand, and that doesn't cost much on the CPU. Some other general recommendation also found in style guides is to avoid throwing exceptions for things that are normal. You really need to throw an exception if there is an error. If, like, you divide by 0, there is something that really shouldn't be happening, and you're throwing an error to the user in the end, then you can use exceptions. But you should not be using an exception instead of, for example, if then else, right? You should really, because an exception costs also some CPU cycles, right? Because of all the things it triggers in the operating system. So be very careful. Do not use exceptions when the code is running normally, right? So try to use other ways. So this is for the CPU scale up. And again, to be very clear, I'm not saying that what you learn in object-oriented programming is not good. This is very good. It helps you write very, very good software. I'm just saying for large scales, when you have billions of times the code that executes, then you need to revisit some of them. It's a general principle in education, and when you learn things, you need to learn the things, and you need to learn when to use them, and you need to learn when not to use them, right? So it's always the wisdom of correctly using the knowledge. Everybody with me? Right, very good. Actually, it's great. I love to play with these things because it's like a video game when you do this, because you have your measure of performance, and every small improvement that you do when you are working on the bottleneck, you see it because it shortens the execution of the code. And these are the most exciting semester project and master's thesis, when you have something as concrete as to optimize the execution, and then you just play Sherlock Holmes and try to find out all the things you can squeeze out of the system. The same goes for the disk, but this you already know, because I've already told you. I told you that if you download from the internet a JSON lines file, for example, and it is very highly structured, so you have a schema that you can build that would validate all of the objects, then you should have this automated thought of validating it and saving it back as Parquet or in an efficient format, because this is going to take up much less space on disk. This means that it's going to be read faster from disk. And it also means that it's going to be able to read just what you need, just the columns you need, and not everything. So the impact of using a binary format like Parquet when your data has a schema is something that really pays off. All the more that the disk I/O is the bottleneck that MapReduce or Spark tries to solve, right? So the impact of that is enormous. Compression can also help, and there are systems that allow you to compress the data using compression techniques from information theory. And again, here you might think, okay, that's going to cost CPU, but again, that's what you do when the disk is the bottleneck. If the disk I/O is the bottleneck, then it means the CPU is a bit idle. So it's totally okay to use a bit more CPU that was anyway idle to decode the data, right? So efficient formats and compression. So it's the idea that if you have a schema, then you should save it to a more efficient format like Parquet. There's others, of course, that are designed, but this is the idea, right? The reason, by the way, I can mention this. The reason why many data sets are available as XML or JSON and not Parquet, you could ask the question, like, why do they not directly give you Parquet? It partly has to do with archiving. for the long term. For example, you might archive data on the ETH library. They have a facility for this where you can put long-term archives. You can publish them in papers. This has to be usable in decades, maybe even centuries for now. You have to think of the people in the future. And when you archive things, you have to be mindful of the fact that the people in the remote future should be able to open them. And if you use technologies that might change rapidly, then you're losing them. They might no longer be able to open the files. And so formats like JSON or XML, they are just text files. So anybody can open them. In the worst case, with a text editor, they would be able to deal with that, right? So this is the reason why, for archiving purposes, we love formats that can be read as text, right? Okay. Then there's the network, right? I told you there's the memory, there's the CPU, there's the disk I/O, and there's the network I/O, right? So now we have the network. The network is really about the shuffling, right? It's when you have to read things over the network. So that's basically in between stages that you shuffle the data. So there's basically two tricks. The first one is to keep shuffling to a minimum, and sometimes to avoid the shuffling. That's the pre-partitioning that I told you about. The advanced users, and really I'm talking about the power users that are really knowledgeable and have a thorough understanding of Spark, they are going to be using functions that other users don't use. For example, there's a repartition function that tells Spark, shuffle things around in such a way that the keys are on this and that machine. You can do it based on hashes, based on intervals. And this is something that is basically not data independent, right? Because technically it's the identity function, logically, when you do that, right? But you're just physically causing a repartition. And that's something an advanced user might do because they know that it's going to benefit the future execution. For example, they know there's going to be a huge and heavy join that is about to be performed. So they are going to pre-partition the data in such a way that the join involves less shuffling, right? That's the idea. That's the same thing I told you with a group by and an order by that normally should each cause a shuffle. But if the order by and the group by are on the same key, then you shuffle only once. That, in fact, Spark can detect automatically. You don't even need to do it manually. Who is with me? Right? So that's the first thing. And the second one that also applies for the disk, it's both for the disk I/O and for the network I/O, is these push-down optimizations. I've already told you about them at least twice, right? The push-down optimizations. That's the ones I told you you will be a hero in your new employer when you do this. It's extremely powerful. Anything you can pre-filter as early as possible to not even read it in the first place, the columns you're not using, pre-aggregate everything you can, pre-project, pre-filter the data as early as possible, because anything you can get rid of, the columns, the rows you can get rid of, the pre-aggregations, that means less data flowing in the network cables, less data to be read and written to disk, like intermediate data. So this is, it's magic. This is extremely efficient. I put here Google Dremel, who read the paper. Some of you should, right? So Dremel is known for a format that is able to map nested data to flat tables. But in fact, Google Dremel is based on that. That's exactly what Dremel does. If I have to summarize Dremel, it's basically a framework that is push-down oriented. It allows you to pre-filter, pre-project, pre-aggregate. And you might have heard of BigQuery. Who heard about BigQuery? Right? So BigQuery is based on this, right? It's not able to do all of SQL because many SQL queries are very, very complicated, but there are simple SQL queries that just select, project, and aggregate in a simple way, and this massively uses push down, right? So remember this, pushing down, that's very, very powerful. The next thing I would like to share with you is an intuition about the configuration of Spark. So now I'm done with telling you the optimizations for memory, CPU, disk, and network. So now let's turn to the optimization of Spark. I'm just giving you an example, and I'll comment on that example. So assume that you have in your cluster 8 machines, 8 nodes. So I'm talking, of course, of virtual machines because you're probably renting them from AWS or from Azure or from Google Cloud. So you have 8 of these machines. Each one of these machines has 16 cores per node, right? And here I mean virtual cores. Again, it's all virtualized because you know that because of hyper-threading, you can actually double the number of cores. It seems that it's double the number. So imagine that you have 16 of them, the virtual cores. Then you have 128 gigabytes of memory per node, right? 16 cores per node and 128 gigabytes of memory per node. You might remember that I told you on the command line when you execute your Spark job with the Spark submit command. So you can basically write a big Java program that you put into a jar file, and then you can use Spark submit to execute that jar file on the cluster. What is there in this jar file? Well, it's basically just creations, transformations, and actions, right? It's just codes that is going to create a DAG and execute it. By the way, it doesn't have to be Java. That can also be Python, or it also works with Python or other languages, right? But anyway, on Spark Submit, you can tell the server how many executors you want, how many cores per executor you want, and how much memory per executor you want. And so that's a decision to make. You need to decide. You have a data set, you want to read it, you have your machines, and now you need to decide on these parameters. And so with this resources available on the cluster, this is an example of how you could do it. You could tell Spark, I would like 24 executors, 24 of them. So Spark is going to figure out that it can put 3 per machine, right? But you basically tell Spark, I want 24 executors. Then you can say, I would like 5 cores per executor and 30 gigabytes per executor. Now, let's do a bit of math, right? So first, how many slots am I going to have if I do it in this way? 5 executors per core. Sorry, 5 executors, 5 cores per executor, sorry. 3 executors per machine, 24 executors in total on 8 machines. How many slots do I have? Yes? 120 is the correct answer. How did you come to that answer? What did you multiply? 3 times 5, so that's 15 cores per machine, times 8, that's 120 slots. Right? So we have 120 slots, and for example, you might have 300 or 400 HDFS blocks that you're reading, and that would sound about right. Is there a question? Yes?
Is the core to slot mapping always 1-to-1?
The cores and the slots, yes, absolutely. Because you have to imagine that a slot is basically a thread. It's a single thread, and every virtual core gives you a thread. It's after the sorry? It's virtual, yes, that's what I'm saying. You already consider that hyper-threading is already used and so on, and you're looking at your virtual code, your virtual cores here, right? That's exactly the idea. All right, so that gives us 120 threads, single threads that can run in parallel to each other, perfectly in parallel, and you should have a multiple of that, the number of HDFS blocks, of splits, so that it works best. Now you're going to tell me, okay, 3 times 5 is 16 per machine, right? How many do I have per machine in total? 16. Do you know why I left one out? Yes? That is correct. So I'm going to repeat on Zoom for everybody to understand. So basically, this core that we are not using, we basically give some air to the system so that it can breathe. Basically, that core, the operating system still has to work in the background. There is a whole system that needs to also orchestrate Spark and so on. And so it's very important to not use everything on the machines, but to leave a little bit for the operating system, right? So that is correct. And you should leave 1 core at the very least per machine, maybe 2, but it's only 16 here, so this is why we are doing this. We are not doing 4 times 4, we are doing 3 times 5, right? Were there comments or questions? I think I saw raise hands, yes? Yes, that is true. We have a lot of processes. Sorry? That's actually a good question. So you're basically saying that since we also need the other processes like the data nodes and so on, do they all run on that one core, or would they share maybe the other 15 cores? I actually don't know. I never went into that level of depth, but that's a good question. Now, maybe you could also consider that if you read from HDFS, you might short circuit the whole thing, right? You might also directly read from the disk. So it might be that then the data node doesn't need to do much. That's actually a very good question that I'll investigate. This data node, would it then run on that one core that is left, or would it be shared with the others? Excellent question. Yeah, thank you for asking. I'll investigate that. But basically, yes, that's the common practice, and that's what you should be doing. Leave one or two cores free for the system to give it some fresh air. And the same for the memory. You should leave around 50%, 20% of the memory free. So if you have 30 per executor, that's 90 gigabytes per machine. You have 128 in total, so that's reasonable, right? You're not using the entire memory of the machine. And you see, roughly, when I pick my executors and cores, why didn't I pick one executor and 15 cores per executor? Or why didn't I put 15 executors per machine with one core? Typically, I take the square root. So basically, the square root of 15, it's integers, right? So that's 3 times 5. 5 times 3 would have worked too, right? So as a rule of thumb, you basically try to take the square roots of the number of cores and to have a similar number of executors and cores. It's only a rule of thumb, right? But don't go for only one executor or only one core per executor, because it's actually useful to have a bit of memory shared across the slots, because that evens things out a little bit in terms of balancing. And yeah, that's the idea. All right, everybody with me? Right, so that's basically the intuition I wanted to give you on a concrete configuration on the machines. Of course, it can be more machines than that. It can be less, but this is the idea, right? Okay. And then, of course, some of you might find one day that they pushed all the optimizations they could and so on, and they really reached the limits, maybe because it's a new use case, maybe it's because the evolution of hardware has pushed us to a direction that is no longer manageable in this way, right? What I'm saying, for example, that now disk I/O is the big bottleneck that we need to deal with, maybe it's no longer to be true in 20 years, right? So for a while, maybe the size of the blocks will evolve. Right now, it tends to increase a little bit every couple of years. And maybe one day, we'll have an evolution of technology that's something inverses, or there's a break-even point that triggers an all new kinds of technologies, and maybe some of you will invent these technologies, right? So you'll be the next ones. But before you do, you need to understand the existing ones, because you need to know exactly why you're building a new technology. Okay, who is with me? Very good. Maybe quantum computers. I keep saying quantum computers, but this might be a very exciting times for implementing operating systems, programming languages, and database systems on quantum computers, if we manage to build them and scale them up. All right, so now I would like to tell you about something else that happens at very large scales and that might be unexpected, at least that's what many people or new employees in big companies discovers, because nobody told them before that. It's a phenomenon that only happens at very, very large scales. You have huge clusters of machines. And so this is called tail latency. So here's the idea. First, you have slots. So in that case, on my slide, I just put 5 of them. I already told you, you should not have one task per slot exactly, because you might think this is what's going to happen, but in fact, this is what's going to happen. If you have one task per slot, you might have one that takes longer and the others become idle. I've already told you that. So that's the reason why you have more tasks than slots, in such a way that you can dynamically allocate the tasks on the slots. Again, every slot sequentially runs the tasks. Those that are slower just will have less tasks. And this one is incredibly efficient, so this one is becoming many more tasks. So you basically spread a little bit the tasks on the slots in this way. So there's nothing new that I've told you, right? Of course, you shouldn't push it. If you say, okay, let's just push it to the next level and have massively more tasks than slots, that's not going to work. It's not going to be efficient. Why? What's going to happen if you do this? What problem will you run into? Imagine you have 1,000 tasks per slot. Yes? Exactly. There will be a lot of overhead switching between the tasks, so a lot of latency, basically. You will basically spend your time switching between the tasks and not less time actually evaluating the task. So this is why this is bad, right? You really need to keep it within reason and have a reasonable number of, more something like this, a reasonable number of tasks per slot. So don't do that. Okay. So it might seem we've solved the problem, and we are able to have our slots finish more or less at the same time, right? And that's going to work with a couple of machines, going to work with a couple of more machines. But in fact, so almost the same, right? You're going to scale up to many, many, many machines, thousands, tens of thousands, and you might think that continues to scale. Bad luck, it doesn't. This is what's going to happen. Totally unexpected, but you will notice on very large scales, tens of thousands, 100,000 machines, one of them is going to take forever. That's called a straggler. And you might think, okay, maybe it's a similar reason than this, right? You might think that, but in fact, no, it's a totally different reason because that's a totally different explanation, the reason why that is actually happening. And this is why what we call tail latency, tail in the sense of the distribution, right? There's a distribution, so this would be a distribution of the execution times. And the tail latency means that it's like a Gaussian, but at the tail, it goes far away and there is one very long execution somewhere. The explanation is, and that's a bit related to what we discussed with the operating system and so on, that the resources on the machine are shared, right? There's plenty of, because of the operating system, the disk, all these resources, there's other programs executed on the machine. They're also shared globally, like the network cables, the distributed file system and so on. And there's a lot of things that are going on in the background. There's background daemons in the operating systems that might have some hiccups. There might be queues. There might be power limits. Hyper-threading also needs to be working in the background. Garbage collection, if you're using Java, can trigger periodically. At times you cannot control. Energy management might trigger and so on. So there's so many things that are highly unpredictable. And the idea is that if you have a huge number of machines, like 10,000, 100,000, you will always be out of luck. And on one of these machines, something happens, and then it just takes forever, right? And here we can actually analyze that. It's surprisingly simple. It's high school math to analyze why this is happening and why we cannot avoid it. Well, we have to find other solutions. So let's take an example. You remember the service level agreements? So it could be that I'm telling you your system has 10 milliseconds of typical latency. So what I mean with latency, some people use it to say, end to end, right? So there's 10 milliseconds. And 1 second is guaranteed in 99% of the cases. So you know that in 99% of the cases, whatever you're doing, it could be the evaluation of map tasks, it could be lookups, it could be, whatever you're doing. You could be analyzing HBase and so on. But you have whatever it is you're doing repeatedly, that in 99% of the cases takes less than 1 second, and in 1% of the cases, it can take more than 1 second. Let's call that probability P, right? So we have a probability P that it takes more than 1 second. P in that case is 1%, right? So let's take 1%. Now, let's revive some high school math in your probability theory. So if P is the probability that you do it once and it takes more than 1 second, probability P, can anybody tell me if I do it n times, what is the probability that every time it takes more than 1 second? So it takes more than 1 second the first time, and it takes more than 1 second the second time, and. What is then the probability that every time it takes more? Yes? P to the power of n. Exactly. That's n, right? It's basically when you have independent, we assume it's independent, so independent events, their conjunction is basically the multiplication of the probabilities, right? The product of the probabilities. Who is with me? Right? Okay, let me ask a more complicated question. That's and. What about or, the subjunction? So what is the probability? Not that every time it would be more than 1%, but that at least one time it will be more than 1%. So now it's or, right? The first takes more, or the second takes more, or the third takes more. What is then the formula? Yes? Yep. This, right? Yeah, exactly. You're correct. You're correct. So we need to take the conjunction of the complement. It's just the magic of logic, right? It's just that when you take the subjunction, it's like the complement of the conjunction of the complements, right? So basically, 1 minus p is the probability that it doesn't take more than 1 second. This is the probability it never takes more than 1 second. That's a conjunction, and then that's the probability it at least once takes more than 1 second. Who agrees with that formula? Right? So this is high school math, I told you. So what that means now, if you apply the formula, that if I just do it once, 1% of the time I'm going to have the issue, 99% of the time I'm safe. So let's now apply this formula with n equals 10, right? So this 1 minus p to the power of n. Now, this gives us that in 10% of the cases, at least one will take more than 1 second, and in 90% of the cases, it won't. So it's a bit worse now, because in 10% of the cases, I'm going to have this issue that there is a straggler. What about 100? So now I have 1 minus 1% to the power of 100, right? So now, in 2/3 of the cases, I have the problem. This is starting to be worrying, right? Because it means that 2/3 of the times when you execute your thing on the server 100 times, you get the problem. Do I have it with thousands? Yes, I have it with 1,000. Thousands, you can forget. That's always going to happen. That's almost like deterministic. You launch your job on the server. You know for sure there will be a straggler and it's going to take forever. That is a big problem, right? So then you might think, let's change the SLA, right? Let's just change the guarantees. What if now I give you the guarantee that in 99.99% of the cases, it's going to be less than 1 second, right? And maybe that solves my problem, right? So let's try. If we try that, now I basically did 1 minus 0.01% to the power of 2,000, and the problem is back. Now with 2,000 servers, that's still a reasonable number of servers in a data center. Once in 5 times, the jobs I execute is going to be a straggler, right? So the problem is back. You cannot get rid of the problem just by trying to have better guarantees. In fact, that's the curves you get. So this is the plot of 1 minus p to the power of n, where n is the x-axis. So the power of that you take is here, and p is just the curve, right? So here you have p equals 1%, p equals 0.1%, so that would be 99.9%, and here you have 99.99%, so p is 0.01%. So you see, you can try all you can to have better guarantees. You always have the problem. In fact, you can actually approximate that if p is very small. What is an approximation of 1 minus p to the power of n if p is very small? You remember the math, how you approximate that, yes? Almost. 1 minus np, that would be the approximation of 1 minus p to the power of n. You agree? And then you take 1 minus that. Yeah. So that's np. np, that's why you have a line here. You see the green curve is almost a line. That's basically np, right? So this is why I'm saying you always have the problem, because that line, it's always going to be linear at first for the small values of p. So you cannot get rid of the problem, right? Who is with me, right? Very good, okay? The trick, by the way, when you have 1 minus p to the power of n, you approximate it at the first order as 1 minus np, right? Who remembers these tricks that you see in analysis with the Taylor decompositions and so on, right? Okay, very good. Anyway, that's just an explanation of why it looks like a line at first, the green curve. All right. So again, you can try all you can. Maybe you try to fix the operating system, or you will not manage. That's just not going to work. This is going to haunt you in the data center. But there are tricks that people found. They just needed to be a bit inventive. And the sort of tricks that they found, it's actually pretty simple, actually. They basically launch every task twice, for example. You just launch every task twice, and whoever finishes first, then you cancel the other one, right? And that actually already is a good fix at first sight, right? So you just duplicate the tasks, and then you cancel the second one once the first is done, right? So that's going to improve a bit the situation. Then maybe you're going to think that's an overkill, right? Here, it's really heavy, right? Because that's a factor of 2, the number of tasks that you're going to execute. So it seems to not be very efficient. So we can do the same idea, but a bit more conservative. So this is the idea that we first launch it only once. So we start launching all of the tasks and the slots and so on. And what happens if one of the slots gets out of control and start being a straggler, then you stop it and you use another slot. You have it taken over from another slot. What do I mean with the 95% percentile, the 95th percentile? What I mean is that you do some statistics. On your data center, you might aggregate statistics of the stragglers. You basically do a histogram of the response times. That gets you something like some curve. And on that curve, you find the 95th percentile. What that means is that you find the response time such that 5% of the time it's more than that, and 95% of the time it's less than that. And once you know that response time, that's 95th percentile, you use that as your criterion to stop the straggler. As soon as you have a slot that takes that amount of time, that would be already in the top 5% of response times, you stop it and you just launch it somewhere else on the cluster, right? We have a question over there. So that is a very good point. So you basically, if I'm repeating for the people on Zoom, you're basically saying, what if the problem is because of the query itself, because of the transformations you're doing and the data that basically triggers that? And you're also making a good point that we do indeed assume for this that the query it doesn't matter, right? It's just some random query. More exactly, what I mean is that it's going to happen whatever query you execute. It doesn't matter what you actually are doing on your cluster. When you have tens of thousands of machines, this is going to be happening. So this is why you're correct to say it's a random query, right? We are not specifying what would you do on Spark or HBase or whatever system you're using. But you're correct that in some cases, the reason why there is a straggler might be because of your query, right? In that case, of course, it's totally different, because if the reason is the query and the reason is not because of tail latency, then of course you should be using other ways to solve the problem. If your problem is the query, then fix the query, right? Because in that case, that's not going to help, because what you're going to execute somewhere else would be the same code, right? So you really need to distinguish, do you have a tail latency problem? Or is your problem specific to the query and the data that you're executing? Here we're assuming that's not because of the query and of the data, that's really because of the background hiccups and on the data center. Does it answer your question? Yeah, very good. Okay. Yeah, we cancel that one, obviously, when that's done. In fact, they tried it. So there's a paper by Jeff Dean about tail latency that I think it's in the Moodle material. It's incredible because, so they did an experience with big tables, so HBase, basically with 1,000 requests just reading a key. So you see it's not tasks and executors here, it's something else, but repeated, it must be repeated. With 100 servers, their percentile, so what I say here with 95% or whatever you pick in here, they said 10 milliseconds. So whatever takes longer than 10 milliseconds, we stop it and re-execute it. And now they went from, without this optimization, it took 1 full second because of one straggler. So it's one of the machines that takes that much, and the others are actually done before. And just doing that, the hedge request, by canceling the one that is more than that and doing somewhere else, you bring it down to 74 milliseconds. That's a huge improvement. And of course, there's a bit of a cost to pay, which is that you have more requests because you need to re-execute it. That's just 2%. You've just increased your number of requests with 2%. And that does the trick. Right. So I think they did it. What I meant here is that they took not the 95th, but the 99.9th percentile to do that. Right. Okay. Who is with me? Very good. Then I just want to check whether that was clear. It was a bit of a break, right? A bit of a pause, because I didn't introduce any new technologies here. I just wanted to make you think about these things, because as computer scientists and data scientists, many of you will be working at that level, and you will have to deal with these things. You will have to deal with performance. Maybe if you do a lab, like, I don't know, the systems lab, or if you work on very large-scale systems, then you'll have to think about all of these things. Right? So, okay, so that was indeed a bit of a break for you, which is fantastic. Okay. Next week, there will be something special. We'll have a guest, Bart Samuel, who is a principal engineer at Databricks, and he's going to come and present to you some of the newest things they have on the Lakehouse and updates and so on. So it will be here exactly at the same place at the same time at 9 a.m. on Wednesday, and so I encourage you to come. We'll broadcast it over Zoom. I don't know yet if it's going to be recorded and shared, because you know how it is in companies. You need to ask the legal department and so on. So we'll see if they accept that we share it. Maybe they'll accept that we share the slides. But anyway, I encourage you to come. Then you can also ask questions, speak with him. It gives you also another perspective, right? Maybe he has a different perspective on things that can be interesting, right? Okay, so I'm going to let you go on that good note with a few minutes early, because you understood it well. So let's celebrate that. Enjoy the exercise session this afternoon and on Friday. And again, if you have questions on Spark, on all the things that I've told you yesterday and the week before, shoot us an email, right? Write to us, ask on the Moodle forum, we'll help you. So thank you very much, and see you next week.